Hello, this talk is on the use of cold fusion excess heat to activate nitinol, which is a shape memory alloy. Cold fusion is real, and active cold fusion systems and components have been available since 1989. They produce excess heat, de novo helium-4, and if they are really producing excess heat, they also produce unique anti-Stokes spectra and radio frequency high Q lines near 327 megahertz. The problem is that driven cold fusion systems are not always active. Active means excess heat is being made, and the distinction is important. It is the same as with an airplane, where, depending upon the angle of the wing, there can either be aerodynamic lift or a stall leading to a crash, and it is important to distinguish the two. I will show you these two states now, both for our LANR type preloaded cold fusion components and for aqueous systems as well. Here is the output of a LANR type component on the right. For comparison and as calibration, on the left is an ohmic control. The blue lines going to the right as a function of time are the electric input power in watts. On the left is the ohmic control giving the same output power as the input, whereas the LANR type component gives much more output than is delivered to it to drive it. This slide shows the rise in temperature divided by input power for an ohmic control on the left and for a LANR type component on the right. You can see that for the LANR type component there are two driven states. At the beginning, there is a lot of excess power that we can see. However, as the voltage is suddenly increased, an electrical avalanche occurs, and yet, even though more electric power is delivered, there's no more excess heat. This shows observably the two states. Also note that the LANR became the same as an ohmic control with the output power matching the input power. This is a second version of the last slide, showing that the ohmic control and the LANR component after electric breakdown are identical in producing no excess heat for either. Excess power gain is only seen prior to the electrical avalanche. As we have shown over several years, coherent Raman spectroscopy not only has a greater intensity at the detector than ordinary Raman spectroscopy, but it can specifically and selectively show the excess heat as anti-Stokes. We can see in this graph that there are three curves. One, when the LANR is off. Two, when the LANR has electrical avalanche. And three, in the desired state, when we have excess heat. Even though there is a much less amount of electrical driving current, here 110 microamps as opposed to 1.35 milliamps after avalanche, there is in the desired active mode excess heat, and it is clearly picked up in the coherent Raman spectroscopy. Active cold fusion systems also give off a radio frequency signal near 327 megahertz, which is near the deuterium line, and this is picked up if a resonant cavity is used, as we taught at the last international meeting. This is only seen with the excess heat. I will now show data in an aqueous system. The data was obtained in the mother of all cathodes unit shown on the right, which in comparison to the size on the left was what we showed at the open demonstration of the Fusor type systems at ICCF-10 in 2003. This graph will show the two states. What we see is an input to an ohma control on the left and to the mother of all cathodes system, 3-liter system on the right, which is aqueous. We can see with the ohma control that with a very large input power, that's the square rectangle, we get a little bit of heat output in comparison to the cold fusion device. When it's working in its active mode, we cannot even see the input power down, which is close to the x-axis. Halfway through, the excess heat production falls and totally diminishes as hydrogen evolution increases. We've been telling you this for years, and here you can see it in front of you. In summary, there are 2 states. They are selectively detected by coherent Raman spectroscopy and by radio frequency emissions looking near the deuterium line at 327 megahertz. And so we get to the point of this paper. In the light that the field of cold fusion needs improved semi-quantitative ways of detecting active components and systems, the question is, can shape memory alloys, such as nitinol, respond to ordinary heat and excess heat, and perhaps selectively detect and distinguish an active cold fusion system? Nitinol was chosen because it is a shape memory alloy and is very different from normal materials. It has a memory and will return back to its austenite phase when temperature is applied. The magic of this occurs because nitinol is an ordered structure. If you took titanium and nickel and mixed them randomly in a melt, they would not achieve what occurs in nitinol, where there are arranged atoms in rows. Metallurgically, this occurs in only one phase, shown here in the blue area. When that select desired phase occurs, this is the analysis that is seen under X-ray spectroscopy. These are the images that are seen under scanning electron microscopy, in that nitinol is arranged as nanofibers of diameter 30 to 70 nanometers in longitudinal fibers, all directed in the same direction, of approximately microns. The desired temperature is chosen at high temperature, approximately 500 degrees centigrade, where the desired shape is set. Nitinol has corrosion characteristics similar to titanium in that it self-passivates, creating a titanium oxide surface layer which protects against corrosion and is biocompatible. For example, here you see on the left that there is a coarctation, that is a narrowing of the aorta of 4.2 millimeters in this young woman. By catheterization, a nitinol device was put into her aorta, and you can see on the right that when it is extended in size, because her blood is hotter than the operating room, the increase in radius went from 4 millimeters to 8 millimeters. That is quite a bit, because for Poisson flow, the blood flow through a vessel goes as the 4th power of the radius. So in these experiments, a straight 1 millimeter rod of nitinol was twisted and put next to, as a sandwich, an ohma control on one side and a nanner-type component on the other, with a temperature sensor in between. This sandwich was covered in boron nitride, which is the soft blue material that looks like clay, and put into 3D printed springs, as will be shown in the next slide. The cold fusion component used was a 7-24 Series 6 nanor, which was able to put out 12 watts thermal output power for an input of 3.94 watts. The core sandwich, consisting of the nitinol wire, the ohmic control, the temperature sensor, and the LANR type component, covered in boron nitride, was put into 3D printed spring systems, also containing numerous sensors. These sensors included thermocouples, a time-of-flight optical measurement system able to give the distance between the ends of the nitinol, a series of accelerometers that were able to give vectorial acceleration. We created an RMS addition, and then by using an effective mass was able to determine the forces that were wrought by the input power. The electric power drive used two systems. The calorimetry has been described in other papers, and we used paradigms to check the algorithm as well. The next few graphs will show that the LANR type component was in fact giving off excess heat. Here we can see the input power in blue and the output power in red. The dotted lines show the energy as a result of the integration of curves, and this must be done in all calorimetry. The ohmic control is on the left and shows output just slightly less than the input, and for the LANR type component there is positive power gain above 100%. Here is another run that shows positive power gain for the LANR type component on the right hand side. This is in comparison to the control, which should be in every graph, and here we see the ohmic control at the left where the output power is identical to the input power. Here is another run that has no separation of the ohmic controls to the cold fusion component. The input power was immediately shifted between the two, and a bracketing sequence was used where the ohmic control is on both sides. Here again we can see that the ohmic controls have no excess heat, whereas the LANR type component clearly has an excess heat that is observable both as a power gain and by energy. This is our final control proving that the LANR type component works, and we can see again in a bracketed system where ohmic controls are on the left and right, but with some separation in time between their operation and the LANR type component. We can see that there is only excess heat for the LANR type component, and this is clearly corroborated by energy as well as output power. The following three curves show that the nitinol is active using an ohmic control alone, no operation of the cold fusion component. This graph shows input power, the temperature differential obtained by applying the input power, and the wrought force on the nitinol caused by the heat. We can see that it lags, but in fact there is a force developed as a result of electric current to the nitinol, and in fact we can see the temperature rise as well. Here again we can see that as a result of input power to the ohmic control alone, we develop both a delta T, which is in blue, and a qualitative force in millinewtons in orange, and we also here measure the distance in millimeters between the ends of the nitinol using time of flight in an optical system which is attached in situ. Here a series of input power steps are given to the ohmic control, and we can see in fact that the time of flight sensor does show an increased distance between the spring ends and an increase in force wrought as a result of the heat from the input to the ohmic control, as the voltage is increased from 7 to 12 volts DC. Here, as the voltage is increased from about 7 3/4 volts to 12 3/4 volts, we can see that at each of the levels, the nitinol slowly increases in distance and qualitative force as a result of the heat wrought from the various input powers working over time through their dissipation. Since we know all of the components are active, this graph shows the difference between ordinary heat from the ohmic control on the left and ordinary and excess heat from the LANR type component on the right. We can see from the top curves, input power in blue and output power in red, that there is clearly excess power coming out of the LANR type component. The forces that were wrought on the nitinol are shown below. These are qualitative forces, and what we can see is that the nitinol is responsive both to the ohmic control and to the LANR type component. And it appears to be qualitatively proportional to the amount of input power for both. This graph shows one of the major problems of nitinol sensors, which is that there has to be an initial amount of heat given to satisfy a phase change before the movements and forces occur. In this case, it can be seen that in the ohmic control on the left, there is nearly no nitinol response in terms of force wrought. Same thing for the first portion of the input power to the LANR type component. It's not until the second region that the phase change has passed, and now the nitinol can respond as expected. This run shows some of the problems with using nitinol, which is that there can be inadvertent and unintended motion. Here, between the ohmic control and the LANR type component, enough heat had passed to cause the phase change prior to the movement between martensitic and austenitic conversion. This was inadvertent and unintentional, and is important to show. In summary, we have investigated nitinol as a possible sensor of cold fusion activity. We built several devices out of nitinol and used both ordinary heat from an ohmic control and cold fusion heat from a LANR type component. That component was able to give a peak output power of about 12 watts when driven for an input power of 4 watts. Looking at the metrics that we could for nitinol, the induced force was the most useful as opposed to length measurements. The nitinol had a derived RMS induced force power response of about 200 micronewtons per watt. However, the nitinol sensors were equally sensitive to both ordinary heat and to cold fusion excess heat. And worse, the sensitivity was only qualitative. The problems of nitinol detectors in cold fusion are that they are nonlinear and that they have a requisite preliminary phase change and that all of their transitions have a hysteresis. In conclusion, nitinol can be a sensor in cold fusion, but it is non-selective for heat. Ordinary heat and real cold fusion excess heat are indistinguishable. Furthermore, the sensors of nitinol are not as sensitive or as reliable and are more difficult to use than other sensors described in our literature. The most important point is that to determine active cold fusion systems, there are only 3 methods: calorimetry using ohmic controls, time integration, and checks of the algorithm and calorimeter, and coherent anti-Stokes spectroscopy, and deuterium-lined radio frequency spectroscopy near 327 megahertz. Thank you.